好, my name is Shengjun Zhou. I come from Wuhan University. It's so glad to have the opportunity to give a keynote talk. Today, I will talk about boosting efficiency of gallium nitride light-emitting diodes. This is the outline of my presentation. I will talk about top-emitting LED, flip chip LED, vertical structure LED, ultraviolet LED, and long wavelength LED. This is a typical LED structure. This is a very simple LED structure. There are many improvements which have occurred to improve the design. Many approaches from improving crystalline quantity of gallium nitride epitaxial and therefore internal quantum efficiency. Many other tricks for improving light extraction efficiency and therefore external quantum efficiency. The typical LED structure includes top-emitting LED, vertical LED, and flip chip LED. Thin-film flip chip LED. Gallium nitride-based LED grown on insulating cell substrate have a lateral current path because two electrodes are formed on the same side of substrate. Current will flow efficiently in only one of the two current paths, depending on the sheet resistance of ITO and N-type gallium nitride layer. To alleviate current clouding around P-type electrode, strip-shaped silicon dioxide current blocking layer underneath P-type electrode was used to prevent current from concentrating on region adjacent P-type electrodes, where any light emitted would be absorbed by opaque P-type electrode. Light output power of top-emitting LED with silicon dioxide current blocking layer was improved by 30% compared to the LED without silicon dioxide current blocking layer. These improvements are attributed to silicon dioxide current blocking layer, which enhance current spreading and reduce light absorption by P-type electrode. Considering refractive indices of gallium nitride and the critical angle of escape cone is about 23 degrees. Only 4% of internal light can be extracted from a surface. Light outside escape cone serves total internal reflection at gallium nitride interface and risking reabsorption. The amount of light trapped in waveguide is 96% of total generated light. The key to increase escape probability is to give photon multiple opportunities to find escape cone. Roughening surface of LED can redirect photons which were originally emitted out of escape cone back into escape cone, thereby improving light extraction efficiency. Roughed P-type gallium nitride surface can improve light extraction efficiency of top-emitting LED. Patent surface substrate was fabricated by combining a semi-reflow photoresist technique and inductively coupled plasma etching. Geometrical shape of surface patterns can enhance light extraction efficiency by scattering or redirecting light inside LED to find escaping cone. A void structure was formed between patent surface substrate and gallium nitride epitaxial layer by combining laser scribing with hot chemical etching method. Light extraction through top facet of avoid embedded LED is increased by 8.9% due to a strong light reflection and redirection by avoids. 3D patterned step-like ITO and with sidewalls integrated into top-emitting LED to improve their light extraction efficiency. Light extraction efficiency of LED with 3D patterned step-like ITO and with sidewall is improved by about 25%. LED emit light in all directions and a substantial amount of light travels downward, which does not contribute to usable light output. To improve light extraction efficiency, distributed Bragg reflect can be raising an array of alternating dielectric layers with high and low reflective indices can serve as back reflect to reflect light that travels downward. To maximize the redirection of emitted photon upward, we combined two single DBR stacks, each optimized for a different central wavelength into double DBR stacks. LED with double DBR exhibits a 30% higher light extraction efficiency than LED without DBR. In flip chip LED, light emitting chip is inverted compared to top emitting LED, so that photon can be emitted from sapphire substrate. Achieving p-type contact with low contact resistance and high reflectance is important to the realization of highly efficient flip chip LED. Current access to the N-type contact layer is provided by metallic column electrodes passing through a plenty of wire holes in flip chip LED, leading to reduced lateral current spreading length and hence alleviated current clouding effect. Light output power of flip chip LED was 26.6% higher than that of top emitting LED at 10-15 milliampere. Transparent ITO combined with distributed Bragg reflect was used as highly reflective p-type ohmic contact for flip chip LED. Direct ohmic contact to p-type gallium nitride was obtained using pure silver after annealing at 600 degrees Celsius. Titanium constant diffusion barrier layer covered onto silver can suppress agglomeration of silver and maintain high reflectance. Vertical LED on silicon substrate were fabricated by combining gold laser lift-off process. Nitrogen polar N-type gallium nitride surface was textured by wet etching solution, which not only improve light extraction efficiency, but also break down Fabry-Perret interference in vertical LED, leading to a lambda emission pattern. TMAH, when etching created prism structure on M-plane gallium nitride to improve satellite extraction of mini LED. Taped isolation trench with an oblique angle of 46 degrees was obtained using a combination of a semi-reflow photoresist mask layer and plasma etching 11 conformal intercollection metal layers coverage across the taped isolation trench in high voltage LED. With storm bridge circuit is integrated into alternating current LED to transform alternating current to direct current for LED, which can only be operated and direct current physically. UV LED have attracted much attention due to their potential application in sterilization, disinfection, and water air purification. Internal quantum efficiency of UV LED is limited by high density of threading dislocation. We compared the effect of different nucleation layers on performance of UV LED. Without nucleation layer, gallium nitride do not measure to form big gallium nitride grains. With low temperature, gallium nitride, aluminum gallium nitride nucleation layer, gallium nitride grows on the C-plane sapphire region and cold region. With Spartan aluminum nitride nucleation layer, gallium nitride only grows on flat C-plane sapphire region. Threading dislocation density in UV LED with Spartan aluminum nitride nucleation layer is much lower than that in UV LED with low temperature gallium nitride aluminum gallium nitride nucleation layer. Due to reduced threading dislocation density, Spartan aluminum nitride nucleation layer can further improve internal quantum efficiency of UV LED compared to low temperature gallium nitride aluminum gallium nitride nucleation layer. This direct writing was applied for fabricating nickel gold wire grid as transparent conductive electrode for UV LED. Nanoscale nickel gold wire grid shows better transmittance than ITO transparent conductive electrode in the UV LED wavelength region. We can see in the figure for nitride LED, the internal quantum efficiency of nitride LED decreases with the increase of wavelength. However, for phosphide LED, the internal quantum efficiency increases with the increase of wavelength. Low temperature growth of indium gallium nitride tube lattice was used to form VPs. Most of threading dislocation are decorated by hexagonal VPs. VPs around TD act as the energy barrier that prevent particles from recombining non-reductively at threading dislocation. VP potential barrier height depends on VP size, which play an important role in determining quantum efficiency of green LED. Compared to square indium gallium nitride quantum well, electron hole wavelengths with function overlap of staggered indium gallium nitride quantum efficiency. Quantum well exhibits a 1.7-fold improvements. Staggered indium gallium nitride quantum well show uniform elemental distribution and better crystal quality, thus leading to a higher light output power in yellow LED. Thanks for your attention.